Welcome to a tutorial on the Smith chart. And what we're going to do here is go through a number of examples where we're placing normalized impedances, little z, and normalized admittances on the Smith chart. So here are 8 examples of the normalized impedances that we're going to look at, and we're going to start with Z1. So let's first of all get the little pointer ready, and we'll place it right at the center.
So the first value we want to look at is 2.0. Z1 equals 2.0. How would you do that, Matt?
Well, we go along the real axis, and my eyesight is pretty bad. I suggest it's there. Let's see if we're right. Z1, there it is, 2.0.
Perfect. Mm-hmm.
Okay, so let's go to the next one. Sam, you get to do this one.
Okay.
Z2 equals 0.4.
0.4. So just to be clear, both the 2.0 we just did and the upcoming 0.4 are purely real values, right? There's no imaginary component to it, and that's why we're not looking at the radially outward circles. We're staying on the center line. So when we do 0.4, you look at the real value axis, and it's right around here.
And there it is, Z2, and I'll just move this over a bit.
Okay.
And let's go ahead then. The next one is 3, so it's J 0.2.
So this one's purely imaginary.
So let's see where it is. It's plus, so it's out here somewhere. And 0.2, well there's 1.987654332, and it's going to be right there. See if that's right. And there it is. And that's on the outer circle that corresponds to Z1 is equal, or Z is equal to 0. So that's right.
Or the real value is
or
equal
the
to
real
0.
value is equal to 0. Okay, Sam, you do the next one.
Okay, so Z4 is negative J1.2. So it's still going to be on the very outer ring, this time at the negative quadrant. So we start at 1.0, we move over, I think this is negative 1.2, or J1.2. And there we are.
Z4. Now the last 4 are mixed, but we know where they are. So Z5 is 0.4. Well, 0.4 was Z2. So we're on the 0.4 circle. There it is. This circle going all the way around.
Mm-hmm.
And it's minus J1.2, so we're in the bottom half. So we did 0.4, and we did minus 1.2. So I think it's right there. And we got to move it over.
Yeah,
there we are. So we're in the right circle for Z, and let's see. Oh,
arrow, yeah.
There we are, Z5. Okay, Sam.
Okay, so just to be clear, because there's both real and imaginary component, we first position it on the real value ring, that's 0.4.
Yeah.
And then we look at the imaginary ring going outwards, which is negative J1.2. So that's how we got this one, right?
Right. And
okay.
now we want to go to plus 1.2, but staying on the same
plus
ring.
0.2.
0.2. Okay,
J
so 0.2, you know where 0.2 is, and we know where that is. I think it's right here. Is it plus? It's plus and plus. So plus 0.2.
A bit over to the
yeah,
side.
so it's plus, oh, that's 5, 4.2. 0.2 is here.
Yeah.
So, and we're on the, that's the
0.4 ring. So it's going to be
0.4 ring. It should be right here.
Yeah.
Let's see if it is.
Great.
Good. Let's do the last 2.
Okay, so Z7 is 2.0 plus J 0.2. So the 2.0 ring is right here. The plus J 0.2 ring. Oh, I'm sitting on it already. So it should be around here.
There's 7.
That's good.
And now the next one is
still on the 2.0 ring, but negative J1.2.
So the 0.2 ring is from Z1. So here's Z1. And now we want to go No, it's not. It's 2 here. That's right. 2 minus 1.2. So minus 1.2. Here's the minus 1.2 and 2. You agree with that, Sam?
Yep.
And we're done. We just traveled around the Smith chart, merrily plotting impedances. So now let's go on to the next examples, which are plotting admittances and impedances, or impedances and admittances. And I must admit that this has been a lot of fun.
I won't impede that thought.
All right, now we're going to look at a series, the same series of impedances, but not the complete set, and show how we get admittances. So the first impedance is Z1 is equal to 2, and it's shown there. Now, we have to do admittances.
So if you actually do the math, the admittance would be 1 divided by 2.0, right? So the admittance would actually be 0.5. How would you get that on the Smith chart?
Well, there's 0.5, so let's see how we get that. Then we can talk about it. So, and there it is. There's the admittance. So what we did was...
So what just happened there?
So we looked at where Z1 sits on a circle concentric with the origin.
Okay.
And then we rotate 180 degrees to get the admittance.
Okay.
And that's all we do. We plot Z1, draw the circle with the right radius all the way around, and go 180.
So you can just do that with any normalized impedance on the chart?
Any normalized impedance. So we're not going to go through all 8. We'll do a few. Let's look at why that is briefly, and that is all a consequence of something we did way back when, and that was when we got the voltage and we got the current. The second term had a minus sign. And so when you flip it, it's just the inverse. And we can do that algebraically, and that's a good exercise, and we looked at it a bit in class as well. All right, shall we go on?
Sure.
Let's go.
Let's try a couple more.
And there it is, 0.5. Now let's look at the next one. Now it's 0.4. So what's the reciprocal of 0.4?
2.5.
2.5. So we predict that there's 2 there. We're on the real axis. So 2.5 should be about there. Let's see what it says. Okay, so we draw our 0.4. And we make our circle about the origin. So there's the radius of the circle, and it goes around. And that's just where this was earlier. And there's Y2. Let's do one more.
Okay.
All right. Next one. So as we said, let's skip that one. Let's do one that's a little more interesting.
The ones that
have
mixed,
extra pieces. Yeah. So there's one. Okay, so let's find this one first. 0.4 is here, and we slide down to minus J 1.2. So that's where Z should be. Let's see. There it is. Now, we draw our circle. There's our circle. We go 180, and there's the normalized admittance, and it is exactly that. Now, it's not so obvious arithmetically, but it's much easier to do it geometrically. Just rotate 180. So we take this, and 180 gives us the admittance, the normalized admittance.
So handy.
So why do we want to use admittances anyway?
Well, I can think of some scenarios. Remember how our lossless transmission line use a conductance for parallel element? Maybe in this case, when we deal with parallel elements, admittance would be easier to work with than impedances.
That's absolutely right, and there's also a practical reason. It's easier to add parallel chunks to transmission lines to make them work properly rather than series chunks, because then you'll have to cut the lines.
That's right.
And that's way more messy. So parallel stuff, parallel circuits, using admittances makes a lot of sense. Let's see if we can extend the idea when we're traveling along the transmission line, and that'll be in the next slide.